Today we're going to talk about Newton's second law. When we're talking about Newton's second law, the biggest idea is the idea that acceleration is caused by an unbalanced force. So it's not just that forces make things move. It's the idea that in order to change your velocity, you need an unbalanced force acting on an object. This is the idea of Newton's second law. We know that acceleration is that change in velocity. So in order to speed up, slow down, or change direction, you don't just need a force, you need an unbalanced force. And what we're really going to do here is we're going to call that a net force. We're going to say that if the forces are balanced, that the net force is zero. So we can write F net equals zero if we have a balanced force. And if we have an unbalanced force, we'll have a net force not equal to zero. And that's going to produce one of these things, some sort of a change in velocity. Now, how much acceleration is produced depends on the amount of mass or how much material is in the object. And let's go ahead and look at this more clearly. So it's that unbalanced force that causes our change in motion or our acceleration. And really, the more unbalanced force we apply, the bigger the acceleration. This is a direct relationship that as one goes up, the other will also go up. If you double the net force acting on an object, it'll produce twice as much acceleration for that object. That's what it means when we say it's directly proportional to. Now, mass is something that will make something accelerate less when there's more of it. So this is called an inverse relationship. We know that the more inertia something has, the harder it is to change its motion. And so what we're going to say is the acceleration does depend on the mass that's being pushed, but it depends on it inversely. Inversely means that more mass causes less acceleration. In fact, if we double the mass, it's going to produce 1/2 as much acceleration. And so the idea here is that for the same net force, objects with more mass won't change their velocity as much. They won't accelerate as much because of this inverse nature of this relationship. So what we basically see here is acceleration is produced by a net force, but it depends on the mass. So it's actually related to both of these. And if we want an equation for Newton's second law, sometimes people call it F equals ma. But on your equation sheet, you're going to see it as A depends on the net force and the mass. And these arrows over the A and the net force indicate that they're vectors and that the direction is important. Mass is a scalar and its direction is not important. And so Newton's second law, people say, is F equals ma, but you have to be careful that F is the net force. And so that is how we're dealing with it. And really, it's not like putting more force on something could cause more mass. That's not true. Your acceleration is a direct result of how much net force is applied, and it also depends on how much mass that object has. So, if the net force acting on an object doubles, its acceleration doubles because of that direct relationship when we're dealing with acceleration and net force and mass. There's a tool for doing this proportional relationship. You can put a box in front of the force and a box in front of the mass. And so put a box in front of the acceleration on top and the bottom. If you double the net force while keeping the mass constant, it will double the acceleration because you kept that mass constant. If the mass is doubled, the acceleration will be halved. We could see that with these boxes as well, this proportional reasoning. that the net force is being held constant, but that mass is being doubled. And so what's happening to the acceleration, that change in acceleration, will be 1 times as much net force, 2 times as much mass. That means we have 1/2 of our original value of the acceleration. Now, of course, if you double both, then you're going to have 2 times as much net force divided by 2 times as much mass, and therefore the acceleration should be doubled and halved, which means that you have the original amount of acceleration of the object. And these are just some examples and how you would do that proportional reasoning. So again, acceleration is caused by a net force and it depends on the mass, but those arrows are now important. Those arrows say acceleration has a direction. Net force has a direction. And the key to this is that they always point the same way. If you know which way your net force is, you also know which way your acceleration is. Knowing the direction of one always matches the direction of others. Those two are linked together. They have to be the same way. We have a few ways of finding acceleration other than using F net divided by mass. You guys did a whole unit where we had velocity time graphs and the slope of that graph was equal to your acceleration. Or we had the shovel, plow, bulldozer, and each of those equations could be used to solve for the acceleration. We're going to be cycling back and using these tools again for this unit. The other thing we know is how to find the direction of the acceleration. Remember that when we draw our velocity vectors, the velocity arrow points in the direction the object's moving. And if the object's speeding up, we would say, okay, maybe it's moving to the right. And if it's speeding up, then the acceleration arrow would also be to the right because they point the same way as each other to speed up. And if the object's moving to the right, in order to slow down, the acceleration arrow would point to the left because they have to oppose each other in order to slow down. We've already talked about mass as well. Mass is material. It's measured in kilograms. And we can use Fg equals mg. Sometimes they'll tell us the weight in newtons. And we can use g as 10 newtons per kilogram in order to solve for our mass in kilograms. But we know that the mass is just a measure of the material in the object, that it doesn't matter where in the universe you are. It also doesn't matter if you're accelerating or if you're moving or not. Your mass should stay constant unless you eat or throw up or change the amount of material that's making you up. Net force is a new word for us. Net force is going to be determined by looking at our force diagram. If on your force diagram you have two forces that are pointing the same way, you would add those two forces together. You would call it the applied force of one object plus the applied force of the other object would equal the net force. So when they're added, when they're pointing the same way, we would add them together to find the sum of their forces. But if forces point in opposite directions, then we would take a force that was going to the right and a force that was going to the left, and we would subtract them. Maybe we have 10 newtons of force to the right and 2 newtons of force to the left. In that case, our net force would be 8 newtons of force to the right. The idea is you use the magnitude of the force and you put them into this equation, that the big force minus the small force is equal to your net force. And so that net force was 8 newtons. And the reason that I know the direction of that force is because it's in the direction of the bigger force. So because my bigger force was to the right, this net force would be 8 newtons to the right. So the up and down arrows should be normal force and force of gravity. And what we see is these two have the same size arrow, which means that they're going to cancel out. The normal force minus the force of gravity would be 0. The net force in a balanced force diagram is always going to be equal to 0. 0 net force means the object's not accelerating. It doesn't mean it's not moving. It could be moving up or down or left or right. It just means it's not accelerating. In this case, our vertical force is balanced, but the force of the person is pushing to the right. And that force of the person is our unbalanced force. So the net force would be the force of the person. It's going to the right, so the object accelerates to the right. Here, our net force would be the force of friction, because again, the vertical force is balanced, but friction is that force that is unbalanced. So we'd say our net force is that friction force. In this case, our net force is to the left, the object is accelerating to the left, but that absolutely does not mean the object's moving to the left. When we have more than one force acting horizontally, we'll take that big force minus that small force. Again, notice how the vertical forces cancel. And so in this scenario, we're going to have that big force to the right minus that small force to the left equal to the net force. And so the force of the person minus the force of friction would be how we would solve for that net force. Now, you guys are going to do an elevator lab where you're going to be accelerating vertically. So again, the up arrow represents the normal force. The down arrow represents the force of gravity. And in order to accelerate in an elevator, you'll need an unbalanced vertical force. And so your normal force is going to be changing size while you're on the elevator to make you accelerate. I could look at this force diagram and tell you right away, I'm accelerating downward. I can tell because I have a net force downward. It is an unbalanced force diagram downward. And so the net force in this case would be solved for by taking my bigger force of the force of gravity and subtracting my smaller force of the normal force. So I would write the equation F net equals Fg minus Fn, and then I would solve for it. And I would point an arrow saying downward for the direction of my net force and the direction of my acceleration. In order to accelerate upward on the elevator, you need a larger normal force than your force of gravity. And so that's how you are going to change your motion in the upward direction. So again, I just looked at this bigger arrow up and I knew I was accelerating up. And so I want to say that my net force is always going to be that big force minus that small force. And so in this case, that big force minus my small force would be found as answer A. Normal minus gravity. So you are going to do an elevator lab, and there are some helpful hints I'm going to give you right now in order to do that. First, I'm going to tell you that first thing you want to do is notice which way are you moving. The way you're moving is the way you point your velocity arrow. In the elevator, the answer for which way you're moving will either be up or down. So you have to figure out which way was the object moving. The second thing you want to determine is what direction should you point your acceleration arrow. You can either pick up, down, or 0. So if you're speeding up, that doesn't mean you necessarily have an upward acceleration. It just means that your acceleration and velocity arrows have to match and point in the same direction. So let's say you're moving downward and you're speeding up. That would be a downward acceleration for that scenario. If you're slowing down, the acceleration and velocity arrows point the opposite way. Use your acceleration arrow to determine the direction of your net force. A downward acceleration is produced by a downward net force. And so you now know that your force diagram needs to be unbalanced in that downward direction, meaning that your force of gravity would have to be bigger than your normal force to make that happen. The last scenario is kind of weird, but you sometimes feel heavy or feel light, even though you haven't eaten or thrown up. That feeling you get as heaviness or lightness is actually the normal force acting on you. You feel heavy when you have a big normal force. You feel light when you have a small normal force. You aren't actually changing your weight. Your force of gravity is going to be constant while you are on the elevator because you won't be eating, you won't be throwing up, you won't be changing what planet you're on. Remember that your force of gravity equals mg, and both of those things are constants. So instead, it's your normal force that's growing and shrinking to make you accelerate on the elevator. Your job is to try to determine, I feel heavy because of a big normal force. I feel light because of a small normal force. And use this guidance as you're trying to go through and do your elevator lap.